I did number one this morning on the help session. So you can go back and watch it and try it on your own. The keys are attached. Let's do one that's similar to this. So let's try page 2. So we'll see a problem like this on the test where I give you a function and you're just going to find the derivative, second derivative, gather your information about relative max, relative min, and then gather order pairs and then sketch it based off your sign line and your concavity sign. Okay, so go ahead and work through this problem and I'll show you the steps and kind of talk through it once you guys get started. The keys are attached. So if you flip over a few pages, you're going to see the key for this problem. Okay, start off by finding your derivative, first derivative. Oops. Okay, common denominator. Vertical points comes from both the numerator and denominator. Set both equal to 0. Use test points. Okay, so we know relative max, relative min, increase, decrease. From here, we can write out our because statements. And I went ahead and I found my locations, order pairs. Eventually, I'm going to graph those points. So 8, 16, and 0, 0. And they all came from the original function. Okay, any questions with A, B, and C? Okay, next part, finding F double prime. Okay, so we can take our F prime, find the second derivative. Clean up that fraction there. Okay, set the numerator and denominator equal to 0, but the negative 8 equals 0 doesn't make any sense. It's just that denominator increases to the 4/3 equal to 0. And divide by 3, raise both sides to 3/4. That should be pretty obvious that it's just going to be x equals 0. And that's the only value that we're going to place onto our second derivative sign line. Okay, we choose values in each subinterval. Test it against the second derivative function. -1. Anything raised to the 4th power is going to be a positive, so negative or positive is negative. +1, also negative or positive is negative. So 0 is a candidate for points of inflection, but is it a point of inflection? No, it's not. Okay. Find where the interval is concave down. So here we have to split this up, right? Because at 0, the graph is not concave down. Concavity is undefined actually. So we have to, so concave down, we got to say -infinity to 0, and then union or comma 0 to infinity, because f double prime is less than 0. Okay, so now we're ready to sketch our graph. We have some important points that we found. All right, 0, 0, and order pair 8, 16. Right, we can go ahead and put that onto our graph. Okay, we know there's a relative minimum at 0 and a relative max at 8. Now, there's something that I want to point out to us here. What's different about 0 in terms of how this graph is behaving? Or where did this critical point come from? From the, where do we pull that information from? The denominator of the derivative. Okay. Now, is there vertical asymptote in this problem? No, because there's no denominator in this problem, right? So if there's no denominator in the original problem, then there's no hole, there's no asymptote, the graph is continuous. But if there's a variable that all of a sudden pops up in the derivative, in the denominator of the derivative, so that, what is that telling us in terms of visually? Okay. Denominator, basically whatever causes the denominator to be 0, or it means what? It means that my slope is what? Undefined. What does undefined slope look like? Sharp turn, yeah. So we're expecting a sharp turn at x equals 0 because of the way that we're pulling it, right? It's obviously not a vertical asymptote, because if it were, then there should be a variable already in the denominator. But this variable in the denominator didn't show up until the first derivative, which means that the graph is fine, it's connected, but there is a place where slope is undefined. It is still a relative minimum, but it's going to be a sharp turn. Okay, that slope, even though the slope doesn't exist, it's still going to be a relative min. Okay, so let's keep that property in mind as we sketch our graph. Okay, so as we sketch our graph, I'm just going to refer to my slope sign lines and my order pairs. Okay, so I have 0, 0, and 8, 16. I can go ahead and plot those. I like to do two drafts of my graph. One where I'm just looking at the movement of the arrows and I'm just following the path of that graph. So I know I want a relative minimum. I want the graph to be decreasing all the way up to 0, increasing to 8 or to x value of 8, and then decreasing after that. Right? I don't really care about my curvature, but I do know that this is the path of my graph. Whatever I do with curvature, I'm not going to veer too far from this path, right? So it's going to be decrease, increase, decrease, and I can't change that. So now that I have that kind of a bit more structure, I'm going to go back and sketch out the rest of my curvature. Okay, I want my graph to be concave down, sharp turn, and then a full concave down after 0. Now notice that I'm not doing a full concave down over here, because why? It's got to be negative slope, right? If I do a full concave down, then all of a sudden I'm introducing a positive slope, which is not part of my description. So I like to have that dotted line to kind of help me make sure I don't veer too far off my path. Right? Because if I do, I know something didn't go quite right. Okay, so sometimes we're not going to be asked to do a full concave down, even though it's showing concave down. It's only a partial concave down. If that makes sense. Okay, so let's practice a problem involving a derivative graph. So if you guys can turn to page I did page 3 as part of our morning review, but you guys can try that later if you like. Let's go to page 7. Okay, so you'll see a problem like this on the test where I give you a derivative graph and I'm going to ask you all this information. So understand that you're looking at the derivative graph. So if I ask you for relative max, relative min, okay, you're not going to be able to look at this and say, oh, that's relative min, relative max, relative min, relative max. Okay. So we have to understand that we are looking at the derivative graph, which is basically the y-axis represents not the location of the original graph, it represents the slope value of the original graph. So the shape of this graph looks nothing like the shape of the original graph. But to help us kind of label what we're dealing with, I like to use these markings here. Anything above the x-axis indicates where my original graph is going to be experiencing some variation of positive slope. You see these you see the graph decreasing, right? These are just indicating that we have a different variations of positive slope that is going to show up on the graph. Anything below the x-axis are just different variations of the negative slope. Anything on the x-axis is where I'm experiencing slope 0 on the original graph. Okay, so let's start off by building our f prime, our slope sign line. Looks like they do give us some endpoints here, -5 to 5. So I'm going to go ahead and place those as endpoints onto my slope sign line. Okay, so what do I target first? What can I place onto my slope sign line? X-intercepts, right? So where do we start? -3, -1, and 3. Okay. Now, the reason that we want to put slope zeros onto our derivative graph is because these slope zeros are candidates for relative max or relative min, right? We want to target these relative max, relative min to kind of help us know where our graph is going to be moving. Okay, so now we want to be able to fill in whether each interval is positive or negative slope. Don't look at the shape of the graph, look at the location. Okay, so having these to the side of your graph is going to be helpful because anything between -5 and -3, where is the graph located? Above, right? Above the x-axis, and we look at our guide here that's telling us that's going to be a positive slope because it's all in the positive region above the x-axis. Okay, between -3 and -1, still above, right? Between -1 and 3, below the x-axis, negative slope. And between 3 and 5, above positive slope. Okay. So now A, B, C, and D should feel easy because you're really just taking the arrows and you're just translating it into because statements. Right. We shouldn't have to look at this graph anymore. Well, at least not until we get to creating our second derivative sign line. Okay, so go ahead and practice writing out your statements, and I'm also going to be asking for because statements on the test. Make sure you're naming your functions and you're providing more than just sign the fact that there's a sign change. For relative min, relative max, you got to specify the order of the sign change. Min is from negative to positive, and max is from positive to negative. Next up, we want to create our second derivative sign line so that we can find points of inflection, concave up, concave down, all that. Now, this is not the original graph, so it's not as easy as saying, oh, I see concave up here, concave down, concave up, concave down. This is not the original graph. This is the derivative graph. So how do we go about looking for points of inflection of the original graph, staring at the derivative graph? The peaks and valleys, okay? So any peaks and valleys, any relative min and relative max of your derivative graph is going to translate to points of inflection. And the reason why that's the case is because a point of inflection is where there's a transition from concave up to concave down. But visually, it's also where your graph is going to be experiencing its maximum steepness, or what should I say, minimum steepness. Okay, so right, so anytime I have a curve here, right, if I'm looking at my points of inflection, right, if you're imagining you're on a roller coaster ride, you're going to be at your steepest point somewhere around here and somewhere around here, right? So these are the maximum steepness or minimum steepness you're going to experience, and that's why they're the peaks and valleys, because the y-axis represents the slope value. So these relative max, relative mins are these where the steepness is at a relative max, relative min. Okay. So we're going to place those directly onto our concavity sign line. So -3, -2, 1, and 4. Now it looks like there's a overlap between slope 0 and point of inflection, which is fine. All right. Now that we have our concavity or second derivative sign line filled out with our critical points, and then we also want to include our endpoints as well. Now we want to be able to fill out each interval in terms of concave up and concave down. But again, we don't want to look at the shape of the graph because this is not the original graph here. So how can I find concave up and concave down looking at the derivative graph? Look at the slope, okay? So wherever I see a negative slope on the derivative graph, that's going to translate to what? Concave down, concave down. I know it looks like concave up, but negative slope is concave down. The reason why is because when the slope is becoming more negative, that's the definition for concave down. The graph is going to have that concave down shape. It's not showing up here, but it will show up on the original graph. And then wherever there is, okay, in concave up, we can pull by looking at where the derivative graph has what? Or slope is positive. Yeah. Okay, so to kind of color code a little bit here. Concave up from -3 to -2, concave up from 1 to 4, concave down from -5 to -3, concave down from -2 to 1, and concave down from 4 to 5. I think this is the hardest transition that students have with these types of problems, and just being able to know how to create the second derivative sign line looking at the derivative graph. Okay, how many points of inflections do we have? 4, because each of these critical points has a change in what? Change in signs, right? So we have 4 points of inflection. We have concave up, concave down intervals. We can write out our statements. Now we can move towards sketching our graph, our original graph. Okay, if you're still copying this down, it's on page 9 of your packet, so you guys have it. let's talk about part H, where we're going to sketch our graph. Okay, so part H says sketch a graph given the points. So the problem does give us some endpoints to kind of anchor from. Now, there's something that has not been, that we haven't done yet, and that is this information here. It says the range is between -7 and 5. What does that mean? Okay, good. So these are the y values of the absolute min and absolute max, right? So however way we sketch our graph, we may need to pull and push on it so that it can fulfill this condition, right? So whatever our graph looks like, we want the lowest point to be at a y value -7. We want the highest point to have a y value of 5. So we can worry about that at the end. But we do need to kind of go back at the end and kind of adjust our graph so that it kind of fits that interval. But right now, we'll just focus on our slope sine line. Okay, we want our graph to move in the way that the arrows are moving. Okay, so the graph is going to rise at -3. What's going to happen with the graph?
Flatten out.
Yeah, flatten out, but then continue to rise, right? Okay, so we kind of have that motion. Okay, at -1, you're expecting a relative max, right? You want a hill showing up at -1, and then at 3, you want a relative min. Okay, so again, it doesn't really matter where your graph is, but we do want to start at these points. Okay, so I'm just going to kind of target my -3. Again, I don't care about my curvature. I just want my graph to kind of move in terms of the slope. Okay, and then continue rising. I want a relative max at -1. I'm going to just pick a random point here for me to build my relative max. And then at 3, I want my graph to have relative minimum. I may need to adjust this later, but at least I have the shape of the graph figured out. And again, your movement of your graph should mimic your arrows, right? Your arrows are telling you exactly how to move. Now, let's go to our second derivative sine line. Okay, we're going to try to give this graph a little bit more detail. Now, we do have points of inflection, -3, -2, 1, and 4, but the y value is not provided. But I still think it's helpful to, okay, your graph may be a little bit higher and lower than mine, it's okay, but go ahead and highlight wherever your dotted graph is, find -3 and just plot that point. Okay, at least it'll give you some target points in terms of when to know where your graph is going to change curvature. So wherever my graph landed at -3, I'm just going to highlight that point. Wherever your graph landed at -2, I'm going to highlight that point. Wherever your graph landed at 1, and wherever your graph landed at 4. Okay, it'll kind of give us some target points so that we know when and how to change our curvature. Okay, so now that I have that in place, I'm going to go over and resketch the graph with the proper curvature that the graph should experience. So initially, my graph is going to be what? Concave down. I know I have to change curvature here, so I'm going to switch over to concave up. Another point of inflection, so I'm going to switch back to concave down. Switch back to concave up. And finally, concave what? Down, but it's not going to be a full concave down, right? My graph is going to be rising, so that's going to help me remind myself I'm not going to do a full concave down because then I'm completely veering off the graph. I'm just going to kind of over exaggerate it, do a little concave down increasing there. Okay, so there's my graph, but now I want to kind of go back and see, does this fulfill my condition for my range? I want the graph to go up as high as 5 and as low as -7. So I may need to kind of adjust this so that I can kind of push and pull on the graph a little bit so I can get it up to 5. And this is too low, right? I need this to go all, because this is set in stone. I can't change this point, but I can change that relative minimum to go, let it go all the way to -7. So I'm just going to just erase this part and just let the graph dip a little lower here. There we go. So the range is kind of like the last thing that you need to do to kind of make sure it kind of fits into that restriction. Okay, any questions here? Okay, one thing I didn't get to is sketching the second derivative graph. Okay, and we'll make sure that we cover that at the beginning of class tomorrow. Okay. Real quick here, before you get your phones here, I just want to just show you real quick. I will send this out to you in a text reminder, but just real quick here, your test on Friday will be this. Okay, so you're gonna have one optimization problem, a box problem where you got to find the minimum top, one derivative graph, we did that today, one curve sketching problem, we did that today, and then you have 3 problems related to topics from your quiz. All right, go and get your phones. No, yeah, your test problem will be like this. Yeah, I kind of skipped over this. It'd be like a box problem where you're going to.